Thank you, Buster. Can everyone hear me okay? All right. My name is Nick Cordisco. I am an electrical engineer and service manager for solar manufacturing. I've been with the company for about 6.5 years. We're a furnace OEM. We design, build, and maintain vacuum furnaces. We have a unique relationship with solar atmospheres, which allows us to learn a little bit more about the customer's needs through some research and development, and allows us to custom tailor design furnace designs for our end customer. Today I'm going to be talking to you about maximizing Quench performance by proper fan and motor and drive selection. And the reason why I'm going to be talking about this with you today is because we just designed and installed our very first super solar Quench furnace out in western Pennsylvania. And we incorporated a new concept that is utilizing a little bit different of a technique that's as compared to conventional design. So, when you design a Quench system, there's different things that you have to consider. Obviously, you need to design a fan that achieves maximum gas flow. When you do this, you want to try to obviously have the largest fan design possible so it can push the greatest amount of gas throughout the system. And another thing that you would like to consider is to have a low flow resistance path. You want to minimize the pressure drops throughout the system to focus your available power of your Quench system on the work and not getting to the work. Another consideration is the type of cooling gases that you need to use in the system. If you're either going to be using a single gas system or a multiple gas system, that needs to be considered. And the objective is to optimize the system's available power throughout the entire range of the furnace. What I'm going to do here is I'm going to basically compare our typical Quench design method or conventional design method as compared to our synchronous design, which we used on our new furnace. So a conventional Quench system design method is typically designed to operate at one pressure, and that's usually the maximum pressure rating of the furnace. When you do this, you sometimes can sacrifice performance because it's only designed to operate for one particular gas at a particular pressure. And when you go lower in pressure, say at -5 or +5 psg Quench pressures, you're not utilizing your full capacity of the system. In turn, that can mean longer cycle times and limitations whenever you use multiple gases in the furnace. When you do use multiple gases in a furnace, you typically design for your best quenching gas. And in this example, I'm going to use nitrogen. So you try to get maximum performance at the maximum pressure rating of the furnace using your best cooling gas. And then when you have a multiple gas system, you typically would sacrifice performance because you're not able to either maintain that same pressure because of the density of the gas, or you could either slow the fan speed down. And obviously when you do either of those, you're not utilizing the full potential of the system. And that in turn can equal longer cycle time. It can even lead to not being able to process certain materials in your furnace. Our synchronous design concept is a little different in comparison to our conventional design, and that is the conventional design usually would be operating at either full speed or below full speed conditions, and that's what's called the constant torque range. And when you're operating lower than maximum rated speed of the motor, you're not utilizing all the available power in the system. In our new design, what we did is instead of using a say 3600 RPM motor, we went down to a 1800 RPM motor and had it specially designed so you could overspeed the motor, so therefore you had to have it specially balanced and rated for overspeed conditions. So what we did is we used an 1800 RPM motor that could be oversped to 3600 RPM. In addition, we had to incorporate a VFD to allow us to overspeed the motor, and then that also allowed us to appropriately design a fan which would be a little bit larger than a typical design, because we want to be able to operate over the entire pressure range of the furnace. Not only to be able to utilize the full capability of the Quench system over an entire range isn't the only benefit. There's other benefits whenever you're using a multiple gas system. And in this example here, I'm trying to show that in the most understandable way. What I did was I'm comparing the conventional design versus the synchronous design. And in your conventional design, when you're optimized for nitrogen gas, you're going to be utilizing the full capability of the pressure of the furnace, and you're able to run that at maximum speed. And what I did is I sort of tried to normalize things to show you the effects of the cooling rate. Cooling rate obviously is a product of pressure and speed, or gas velocity. And when you take the two variables here, pressure and speed of the furnace, you multiply them together, I came up with a number of 7,200. Now, if we put our synchronous design in the same furnace, same application, you're going to notice that even though we're using a 1800 RPM motor, we're able to spin it at 3600 RPM, still at the same pressure, and obviously you're going to come up with the same product of your pressure and gas velocity, 7,200. So when you compare the two here, you're equivalent in your relative cooling rates. But the benefit in this synchronous design here, when you're using a multiple gas furnace, is when you don't have a VFD or a motor that's capable of running over speed and in the synchronous design range, what you have to do in some cases is drop the pressure back because the gas is heavier, you can't move, or you're going to overload the motor at the higher pressure, so you therefore need to drop the pressure. And in turn, what you do here is the net effect, whenever you multiply the two, is a lower number. In our new system, what you can do is you can obtain the pressure that you would like to use, and therefore your density is going to be a little bit higher because you're using a different type of gas, and you drop the speed back ever so slightly, but yet you're still in the constant, or the synchronous speed range of the furnace. So you're utilizing the full horsepower and the full potential of the system. And as you can see here, the net effect when you multiply the two is a larger number. So when I compare those two numbers, in effect what you're getting in this new design is a 24% improvement in relative cooling rate when you're using the different gas. That could mean you could process different types of materials, and also you can run shorter cycle times. What we did here is to do some testing of the conventional design and our new 20-bar design, was to use a standard cooling or a standard quench, or a standard load, sorry. And the load consisted of 20 steel bars, 3 inches in diameter, 28 inches long. We had 6 baskets, 1 grid, and it was an approximate weight of 1,300 pounds. We measured the thermocouples in various bars, and what we did is we averaged the cooling temperatures of the work thermocouples and came up with average curves to better describe to you what's going on in our tests. Our test procedure, we used the same load to minimize any variables. We used nitrogen cooling gas, and we brought the load up to 2,000 degrees, quenched from there, and we varied the pressure and obtained data at 2, 4, 6, 10, 15, and 20 bar. As well as we also compared one of Solar Atmosphere's best quenching furnace, same size furnace, 5748 size furnace, and we compared the two at 10 bar as well. As you can see here, the 2 lines on the left are the control thermocouples, and which isn't really important in this scenario. But what I do like to stress here is the cooling rate of the load compared from the best quenching 10 bar conventional design furnace here on the right to our 20 bar design at 10 bar. And as you can see, say from 2,000 down to 1,000 degrees, we improved the cooling rate by over 2 minutes, which is, as we all know, is great. The next test that we did was we varied the pressure in our 20 bar design to test the different cooling effects based on pressure. We did, like I said, 2 through 20 bar, and as you can see, the cooling rate improved greatly. The curve on the right is 2 bar, and as you go across, 4, 6, 10, 15, and 20 bar. One thing I would like to stress real quick is from this previous design, what we were able to achieve in a 10 bar furnace, say from 2,000 down to 1,000 degrees here, we were able to cool the load in approximately, 8 minutes. And when we compare that to our new design here, we were able to achieve the same cooling rate, actually a little bit better, just using 4 bar in this design. It's an extra added benefit because you have to use as much gas to get the same cooling rate. Well, in conclusions here, what I'd like to stress here is incorporating a VFD into the Quench systems allows versatility, not only in operating over a different pressure range, but it allows you to also utilize the full potential of your available system when using even multiple gases. And also I'd like to stress that operating at synchronous speed or above is also ideal because you're utilizing the full horsepower rating of the motor, and therefore you're able to get better quenching speeds. And that also allows you to use the largest possible fan to increase your efficiency of the system. That was about it. That's all I had today. I'd like to thank Bob Wilson and Riyal Ferret for their contributions and support, and would like to entertain any questions at this time.